Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my greatest pleasure to welcome Zhao Le back to Microsoft. Many of you probably overlap with Zhao Le as he was a former ISRC intern in our group working with Chao Liu. But we all remember that Le is actually from CMU in the LTI, Language Technology Institute, CMU, a very famous institution in the HLT area. And for those of you who are active in the TREC community, you probably already know him. Le is a very active contributor in the TREC community, contributing to the Lima toolkit, and his earlier work spanned from the structured document retrieval to the recent one, most recently on this term mismatch problem. But in addition to that, Le also is he's from LTI, so he's also well-rounded in the HLT community. So he has done work in patent retrieval, biomedical documents retrieval, and today he's going to tell us his PhD thesis work. So without further ado, Le.
Hello, everybody. I'm really glad to be here again, to see my old friends here and to make new friends. And I'm especially glad to see a reasonable turnout on a Monday morning. In this talk, first, before I begin with the talk, I want to comment that I know there are people joining through the video link, and there's no way for you to participate in the question answering session. So I listed my email up here. You can send your questions through my email, and I'll try to get to them at the end of the talk. Okay. So this talk is about text retrieval. And let's first see what is text retrieval. The task is a confused user generates a query which contains certain query terms to a retrieval engine. The retrieval engine returns a set of results from a document collection and feeds back to the user. So hopefully the user will be happy with the results. This task and the retrieval engine is usually evaluated using a Cranfield style evaluation, where this evaluation abstracts away the user by retaining only the query that the user issues, and retaining only the results that the users are happy about, which are called relevance judgments. And these relevant documents help us evaluate, together with the queries, help us evaluate the retrieval engine in a relatively objective way, an automatic way. So here comes the big question. Where are we, and where are we going? The current retrieval models dates back to the early 1970s. The best ones are still from the 1990s. These current models are based on simple collection statistics like tf.idf. TF is term frequency, which measures how frequently a term occurs in a result document, and IDF basically measures how rare a term is in the collection. So what these retrieval models doesn't do is any kind of deep understanding of natural language texts. So given this current status, what's the ideal length like? What's perfect retrieval like? Given a query, information retrieval, given an answer, text search, a perfect retrieval model should be able to judge that text search implies information retrieval. And that is called a textual entailment task, inferring whether one sentence infers another sentence. And is known as a difficult natural language processing task. And also, searchers are frustrated frequently when they are doing informational searches. So we're still fairly far away from the perfect length. But what problems have been holding us back all those years? And this work argues that perhaps the following two central and long-standing problems in retrieval are the culprit. One is called the term mismatch problem, where query terms fail to appear in relevant documents. It happens sometimes because people describe the same thing using different vocabulary. And this general vocabulary mismatch problem is studied in the 1980s when Sue was still working for Bell Labs. So that's how long-standing this problem is. However, there is still no clear definition of term mismatch in retrieval. The second problem is query-dependent term importance. If you're familiar with retrieval models, it's the probability of a term T occurring given the relevant set of documents. So the probability of a term T occurring in a set of documents relevant to the query. Traditionally, term weighting is assessed using IDF, basically how rare a term is in the collection, because it has nothing to do with the query. It has nothing to do with relevance. This probability, PTR, is known to be important for retrieval. It's known to improve retrieval a lot. It appeared very early on and have been studied by scarce research. And these research provided very few clues about how to accurately estimate this probability in a query-dependent way. This work connects these two problems, shows that they can result in huge gains, and uses a predictive approach to try to solve both problems. And in this talk, I will use term mismatch problem as a thread, because it's a more general version of two problems, as I will show. First, what is term mismatch and why do we care? In job search, you might be looking for information retrieval jobs on the market, but job posts could as well say text search. This could easily cost you potentially 50% or even more of the job opportunities, even if you are careful when you are formulating your query. In legal discovery, you might be looking for bribery or foul play in corporate documents, but they will never say that. At most, they will say grease or payoff, and this could cost you cases. In patent application search, it could cost businesses. In medical record retrieval, successfully finding the record, regardless of vocabulary mismatch, could potentially save lives. So in areas where the user cares most, mismatch can hit most. People know that mismatch is an important problem, and they have tried to solve mismatch from different angles, from the documents end, from the queries end, or from both ends. Our approach is different. So suppose you are given a problem, or any question, any problem. How would you proceed to solve that problem? Right? What's your first step? The first step is always to clearly define the problem, what the problem is, and then to see if it is a real problem. So in this case, I will show you that in theory and in practice, this is a real problem. And then we should try to understand the underlying mechanism of how this problem is created and try to solve the problem using principled ways. So I promise to show you these in this talk, and I will come back to this slide throughout the talk so that you know I fulfilled my promise. So first definition. We define the probability of a term to mismatch relevant documents to be the probability of a term not occurring in the relevant set of documents relevant to the query. So suppose we have a collection of documents here. The larger bubble represents the documents that contain T. The smaller bubble represents the documents that are relevant to your query. Mismatch is the proportion of the relevant documents that do not contain the term T. So if you use the word retrieval as your search term, then these will be the jobs that you mismatched in all the relevant jobs on the market. So first, I want to comment that the term mismatch probability is related to the term recall probability, which is just the complement of mismatch. So recall is the complement of mismatch. Secondly, this probability can be very directly calculated if you know the relevant set of documents for a query. So if you have relevance judgments from queries, you can accurately estimate this probability. Basically, how many relevant documents doesn't contain the document T divided by the size of the relevant set. Now, let's look at some examples. These are some queries and query terms, and these are the term recall probabilities for these query terms in the query. So for the word spills, in oil spills, it occurs in 99% of the relevant documents. So it has a very high recall, low mismatch. Why is that the case? Perhaps there are no other ways to describe oil spill. Yes, question.
How do you know which documents are relevant? Did you manually label them? Okay.
Yes, the user manually labels the documents, and then we collect those. Thanks for the clarification. So perhaps there are no other ways to describe spills except oil spills, because oil leaks means something else. Term, limitations. Term. The word term appears in 98% of the relevant documents. Perhaps there are also no other ways to describe the word term here. However, the same word term in long-term care appears only in 68% of the relevant documents. Why is that the case? Because long-term care can be described as elderly care or home care, etc. So it's not really a necessary term for relevance. The word effects appears, it's an abstract term, and it only appears in 28% of the relevant documents, because effects could be described as improvements, decrease, impact, etc. Ailments is not only abstract, but also a rare term, and that makes the situation much worse. So these queries are from TREC datasets, where the government provides users to generate the queries and do the assessments to generate relevant judgments, and we as participants can freely participate and evaluate our systems. So this is a very nice deal. So by now, there should be a lightning strike in your head. We have a very simple definition, which allows us to estimate the probability of mismatch from relevant documents and to analyze mismatch. This probability, the probability term occurring in the relevant set, occurs in one of the very early retrieval models. If you assume that term occurrences are binary and conditional of each other given the relevant information, then the Bayesian optimal ranking score is given by this formula. If you're familiar with machine learning, this is just the naive Bayes model. The retrieval model aggregates relevant scores for the terms that have appeared both in the query and in the document. And we are scoring whether document D is relevant. And in this case, two conditional probabilities determine, two sets of probabilities determine this retrieval score, and two probabilities determine the optimal term weight here. One is the probability of a term occurring in the non-relevant set. Because the relevant set is usually very small compared to the collection, this probability can be accurately approximated by the probability of a term occurring in the collection, and results in the traditional inverse document frequency based term weighting. So term weighting based on how rare a term is. If it is a rare term, it is more important. The other part we now know is determined by the term recall probability. Now, this is a very basic model. However, more advanced models use this as the sole part, as the only part that specifies term weighting, how important a term is. And other advanced models behave very similarly. And these more advanced models have been used as very effective features in web search. And to recognize that, it is important to recognize that this probability, the term recall probability, appears as the only part in the query that is about relevance. This part has nothing to do with relevance because it's a collection statistic. It has nothing to do with the query. This full formula has been called relevance weight or term relevance, but term recall is the real part about relevance. So in theory, it's as important as IDF, and the only part in a retrieval formula that is about relevance. In practice, because people know this probability is difficult to estimate, you need information from the full set of relevant documents in order to estimate this probability. So people typically just ignore this part and only using IDF-based term weighting. And when people do that, it causes the emphasis problem, where the retrieval model will try to emphasize the high IDF terms in the query. So for example, for this query, prognosis of viability of a political third party in the US. Prognosis and viability have the high IDF. They are rare terms. So they are being emphasized. If we look at the term recall probability, political third party should be emphasized instead. When the retrieval models assign a wrong emphasis to the query terms, there could be top false positives, where this is a rank result given using an advanced retrieval model, language model. And all these top 10 results are false positives, meaning they're irrelevant documents that happen to contain the rare terms, prognosis and viability, but they are not about they're not about the topic. And it's important to recognize that this is an emphasis problem instead of a precision problem, because if you just look at the top results, right, you see that prognosis and viability are being used about something else instead of political third party. So you might think that if you require prognosis and viability to be about political third party, it might improve the situation. But in fact, increasing the match, strictness of the match, can only increase mismatch and can make the situation worse. So this is a mismatch problem, not a precision problem. Recall, not precision. And even Google and Bing still have top 10 false positives. I should note that Bing is behaving much better 2 years now than 2 years ago when I first tried this query on Bing. And Google actually decreased performance a little bit on this query. I don't know why. So false positives throughout the rank list, decreasing precision at all recall levels. But I've shown you that this is an important problem, but how frequent does it occur? How significant is the problem? Turns out, in the 2003 RIA Reliable Information Access Workshop, it gathered many groups of experts, research IR systems, top research IR systems, evaluated language models, BM25, pseudo-relevant feedback, all the very standard techniques that are still being used now, and did a failure analysis and discovered that out of the 44 failed topics, 64% of them, so we are summarizing their results here. They did not summarize their results that way. Out of these failures, 64% are because of emphasis. And we now know that recall-based term weighting can help solve this problem. Another 27% is the mismatch problem, where you need kind of a query expansion to solve the problem. And we now know that if we know which terms tend to mismatch, we can guide our expansion toward solving these problem terms. So underlying more than 90% of the failures is our need to predict this term mismatch probability. So in practice, it explains common failures of retrieval models. Not only that, but also many other behaviors of the retrieval techniques, such as when you are combining bigrams with unigrams in your query. The bigrams tend to have a much lower weight than the unigrams. Why is that the case? Because the bigrams increase mismatch, right? So they should have a much lower recall probability and much lower weight than the unigrams. And personalization, word-sensitive disambiguation, and structural retrieval, which enforce structural matching between the query and the documents. These techniques all increase precision and are shown to be less stable for improving retrieval. Why is that the case? Perhaps the problems that the queries are suffering from are the mismatch problems, not the precision problem. Okay, I've shown you that it's a frequent problem. Now let's focus on the emphasis problem. It's a frequent problem, but what about retrieval performance gain? Right? What kind of gain are we talking about? For basic models, if you apply the true term recall probability into the retrieval models, it can get 100% gain in retrieval. In more advanced models, it can still get 30 to 80% gain. So for a new query without relevance judgments, we need to predict that probability. But that prediction perhaps doesn't need to be very accurate to show a performance gain, because there's a huge potential. So huge potential of gain. Now on to prediction. How do we predict this probability, this mysterious probability that people find no clue to predict? Very few clue. We look at the data. Right? First, it varies from 0 to 1. So we need prediction. Second, the same term in different queries can have different term recall probabilities. So we need a query-dependent way to predict this probability. Third, it's different from IDF. These three trends also occurs in more larger scale analyses. Here, I'm listing the term recall probabilities. Each point is a term, the term recall probability of a term, sorted in descending order. As you can see here, the term recall probability varies from 0 to 1, almost uniformly. This is from one TREC dataset, which includes 50 queries. So these are fairly long queries. For shorter queries, the term recall probability, there's a bias toward higher recall. And you should be surprised to see this statistic, because on average, a query term mismatches 30% of the relevant documents. And that's a query term from a short query. So imagine you are, as a user, you are typing into your search engine one query term. You are excluding 30% of the relevant documents. And as you type the next term, you are excluding another 30% from the remaining. Right? So that gives you less than 50% of the relevant set to even begin with.
Here, when you compute the term recall, you're assuming exact match. You are not doing any stemming.
Good point. I'm doing stemming. Yeah. Crowvet stemming. And globally, the plotted here are the term recall probability, the mean, and the variance of the term recall probability for the same term that occurs in more than one query. As you can see, it still varies from 0 to 1, and the spikes are the variance. So for a lot of the terms, there is a variance, but the variance is small, but it could be large for certain query terms. I'm plotting here, the points are the query terms, and X is the DF or IDF, Y is the term recall probability. As you can see, there is a slight correlation, but it's still messy. So you cannot directly predict this using IDF. But what have prior approaches done? Prior approaches have tuned this as a constant or use IDF as the only feature to predict. And success is limited over only very basic models. And the missing piece is the knowledge that this probability measures term recall and is related to term mismatch. With this knowledge, we can ask ourselves, what causes mismatch? What might cause mismatch? First, a term being not central, or a concept being not central to the topic. The words related or potentially related are not really central to this topic. Propounded, not really central. So these terms tend to mismatch. Second, synonyms tend to occur in place of the original query term, causing mismatch. Abstract terms tend to be replaced by more specific terms in relevant documents and cause mismatch. And given these factors, we can try to design features to model these factors and to do prediction. So I've shown you the mechanism of how mismatch occurs and how mismatch causes problem in retrieval. In terms of features, what we need to do is we need to identify synonyms of a query term in a query-dependent way. We've made specific choices in our design of the features to be general, to only depend on the query and the collection, so not to use external features, external resources. But certainly, it's not the best way. There should be better ways to design these features. But this is the first set of features that have been shown to work for this problem. And let's see how we do that. So first, external resources like WordNet, Wikipedia, query logs, they have a coverage problem, and they tend to be more static, not query dependent, so they're not easy to use. Using them are research topics themselves. What we did is use a term-term similarity measure in the concept space to help us identify the synonyms. So it's called the local latent semantic indexing because given the query, we do an initial retrieval, get the top set of documents from that retrieval, and apply latent semantic indexing on that top documents. So for example, we can get top 200 documents, do dimension reduction, keep only 150 dimensions. And here are some examples. This is the query term. These are the top similar terms identified by latent semantic indexing. So we use as a feature the self-similarity. So we use inner product as a similarity measure. We use the self-similarity of the term as one feature. That measures how well the term correlates with the latent concept space. And the latent concept space is related to the query, so how well this term relates to the query. We also use as features the average of the supporting terms, average similarity of the supporting terms as a measure. So basically, we're also requiring that not only the term correlates with the topic, but also the supporting terms. Basically, the concept is central to the topic. And also, we design a feature which measures how likely these synonyms replace the term in collection documents, right? If the synonyms are frequent terms, then it's very likely that these terms will appear in documents that the original query term doesn't appear in. So these are the features. And we can measure.
Sorry,
yes.
Can you go back a slide?
Yeah.
I didn't understand number 2. What are supporting terms?
Supporting terms are the top similar terms measured by latent semantic indexing. So basically, we represent each term in a concept space, and we compute inner product similarities and rank. Rank the terms, and these are top similar terms.
So you simply pick, let's say, top 5 terms.
We pick a top 5. Yeah.
And then, sorry, I didn't understand 3 either. So synonyms are also the supporting terms? Or?
Yes, synonyms are the top supporting terms. And we are measuring how likely these terms occur in collection documents that this term doesn't occur in.
It doesn't occur in. Okay.
As a measure of how likely these terms replaced the original query term in collection documents.
The collection is it's the collection of the entire.
The entire collection, yes, not just the top documents. We can measure how well they correlate with the target term recall. Turns out term centrality has a fairly high correlation because IDF has a 0.13 correlation, right? Negative also means helpful. Positive or negative. As long as this absolute value is large, it's helpful. Centrality, concept centrality, also very helpful. Replaceability, well, understandably, it's negative correlation. And it's fairly high. Abstractness. The abstractness feature is based on the observation that users tend to modify more abstract terms using more concrete terms. For example, educational is being modifies the word program in this query. So program tends to be the more abstract term, and so on. Effects also tend to be an abstract term. So we can use a dependency parser to parse the query. And if a query term is being modified by other query terms, then we say this is more abstract. This is a binary feature, and it has a correlation of 0.12 with the target. So this is also very helpful.
Sorry, and the top documents are retrieved using just IDF?
Using the baseline retrieval model, whatever baseline I'm comparing to.
So you are using a dependence parser. So which dependence parser?
Stanford.
Stanford dependence parser.
Yeah.
But the Stanford parser is not designed for queries, right?
No.
So what's the accuracy of your dependence parser?
I haven't verified, but for the small set of queries that I looked at, the parse looks very accurate. So the parsers also behave fairly accurately on short texts. So given these features, we can model the prediction of term recall as a standard regression problem. We can use training data with known relevance, training queries with known relevance to train the model, and use another set of queries without relevance information as the test set. And here we use Gaussian kernel support vector regression as the prediction model. You can also use other advanced prediction models like boosted decision tree or boosted regression tree. It works similarly. And in experiments, we are measuring two things. One, how accurately we are predicting term recall, using how closely the prediction is from the truth. Second, we are measuring retrieval performance, using overall retrieval success and precision at top ranks. So what percentage of the top 10 are relevant? So here's one example. For this query, we are getting the correct emphasis here, although the absolute value is still not very close. And more globally, this is the method that uses the training set average to predict for the test set. It gets an error of 0.3. So suppose the distribution is uniform from 0 to 1. The term recall is uniform 0 to 1. If we use the training set average, it should get an error of 0.333. So it's not completely uniform. Using IDF alone increases error a little bit. Using our features and tuning the meta parameters of our features, we can reduce error by half. And this shows if we use the recurring terms, the terms that occurred in more than one query in the training set, to predict. So use the previous occurrence to predict the next occurrence. We can get a fairly low prediction error. But these two values are not directly comparable because they are not measured on the same set. Right? This is measured on test set. This is measured on the training set. So it can be predicted. And I want to just briefly insert that our method demands a more general view of the retrieval modeling problem. Traditionally, retrieval modeling is seen as restrictedly as a document classifier for a given query, to classify whether a document is relevant to the query or not. The more general view sees a retrieval model as a meta-classifier, which is responsible for many queries. It takes in a query as input and outputs a document classifier. So given this view, learning a retrieval model basically is just transfer learning in machine learning. Right? We're basically using the knowledge from related tasks, training queries, to classify a document, learn a new classifier for the test query. Our features and model are just facilitating the transfer. So this more general view would perhaps lead to more principled investigations of the problem of how to learn retrieval models, and also allow us to apply more advanced transfer learning techniques into retrieval. Okay, that's the insert. We're measuring retrieval performance now. If you are familiar with the retrieval models, this is how we insert the probability into the retrieval models as the term weighting, in language model. If you're not familiar with retrieval models, it's okay. We're just weighting the query terms. We're not doing any kind of expansion. And this is the performance on 6 different test sets. Each test set from TREC contains 50 queries, and we're using one as a training set and one as a test set. And across board, there is a 10 to 25% gain. Most of them are significant. So this is measuring overall retrieval performance gain. And in top precision, as predicted by theory, there's also a 10 to 20% gain, although not always significant because the measurements are sparse. So it can be used in retrieval as term weighting to help solve the emphasis problem and leads to significant gains. What about the mismatch problem? Right. If we can successfully solve the mismatch problem, increasing the term recall probability of every query term, we can at the same time solve the emphasis problem. So let's recap.
Just want to clarify. In order to use your technology, you need to two-stage retrieval.
Sorry?
You need two-stage retrieval.
Oh, yes, yes. We need a two-stage retrieval, one to generate the features, one to do the retrieval.
Given a query, you need to first of all retrieve a set of pseudo-relevant documents.
Yes,
Then
yes.
general features and then apply the model to weight these
Yes,
terms.
yes, 2 stages.
So have you ever compared your method with just pseudo-relevance feedback?
Yes, that's a good point. I do have, but I'll come back to that after the talk.
So the slide you were showing on the transfer learning, or can you go back to that? Sorry to keep going back.
No, it's
So this more general view that this is sort of like a learning, are you saying something different? So most retrieval models now are usually learned given sort of a training set and a test set. Are you saying something different from that? Or?
good point. So right now, there's the dominant model is learning to rank.
Right.
Basically learns a global retrieval model out of the training set. So just one retrieval model. So basically one classification model. Right? And applies the model, the same model on the test queries. But here we're learning from these training queries and generate a new classifier. So the classifier is different. While the learning to rank learns a global model, one classifier. Does that answer your question?
No. So the classifier in your case is the product of the P of T given R's, or do you actually have an underlying model as well in addition to those?
The underlying classifier is just BM25 or language models, which is just the traditional models with that probability inserted into the model.
Right, so what you're doing is you're learning an improved probability.
Yes, but that's at the same time with a different term weighting. That is a different model, right? That is a different classification model. It's the same retrieval model, but there's a different classifier because you're classifying the documents differently with the different term weights.
This retrieval is too thick.
Yeah, no, I understand that. I mean, I can ask you more about this later. It seems seems more like different feature values to me than a different model, but I'll ask you.
I can perhaps come to that later. So let's recap. Mismatch. Mismatch ranges from 30 to 50% on average. Relevance matching can degrade very quickly for multi-word queries. The solution, one solution is to fix every query term, right? If we fix every query term by expanding every query term using its synonyms, it results in a conjunctive normal form query. So in this case, this keyword query is being expanded into a conjunctive normal form query. It's very expressive and very compact. One conjunctive normal form query in this case is equivalent to hundreds of alternative queries using keyword queries. This is used very frequently by lawyers and librarians. In this case, it's a query, legal TREC query, which is created by lawyers. As you can see, they spend lots of time trying to expand every query term. So it's a very tedious task. And what we propose to do is, given this term mismatch probability, given the prediction, we can help guide the expansion to focus, to let the user focus on the terms that have the problems, right? So here, placement and children are being expanded and keeping the other terms untouched. The goal is to expand let's say 2 terms, and still getting 90% of the improvement. That would be great. So how do we evaluate that? Ideally, have a user. We let the user propose a keyword query. Keyword query is sent to the diagnosis system, being diagnosed, which are the problem terms, and the problem terms are being fed back to the user. The user expands the problem term, and the query formulation strategy generates the query, submit to the retrieval engine, and do evaluation. So in this case, we can have different diagnosis methods in the diagnosis component. And we can have different query formulation strategies in the query formulation component. And we can compare these different methods. That's what we intend to do. However, online user studies of such a complex system need to control many variables. Without millions of users, this kind of online study cannot be carried out. What we end up doing is a simulation. We have the expert user give us a fully expanded CNF query beforehand. We extract the keyword query by taking the first term out of each conjunct. Similarly, the pipeline goes. So this is one simulation. And the user expansion is also one simulation where the expansion term is being extracted out of the existing CNF query. So this simulation is fairly realistic. It uses full expansions to evaluate partial expansions, to simulate partial expansions.
I'm missing something. Why is it bad to expand everything?
It's good to expand everything, but I'm just saying that given our probability, how are we using that? Well, we can use that to guide the expansion, to save some time for the user.
But so I don't think the user, I mean, the expansion happens automatically, right? What does the user do?
Oh, the expansion doesn't happen automatically. So the CNF query you're seeing is being expanded by a lawyer, spending lots of time on one query.
But I mean, you know the synonyms, right? I mean, we have dictionaries with synonyms. Right? I don't understand what's the manual part here.
The synonyms are difficult to get. These are the gold. If you can get the synonyms, you get great retrieval.
Okay.
But we don't. We don't have automatic ways to get that. Yeah, perhaps Bing has that.
Okay. I thought that. All right. Okay.
But even Google and Bing have this problem. So that means if we can manually expand more terms, right, we can do better.
You actually think the manually generated CNF queries give you the upper bound, right? The proposal.
Yeah. So I'll show the experiments. So here we are using two data sets, one with CNF queries created by lawyers, one with queries created by search experts. In terms of retrieval, in terms of diagnosis methods, right? I'm plotting here on the x-axis the number of query terms that are being selected for expansion. On the y, the retrieval performance gain, the relative performance gain. So the upper bound is expanding fully or expanding not so full, but close. So a fully expanding sort of give an upper bound. You can observe here, these 2 points are using the PTR-based diagnosis. So predict PTR and do diagnosis and do simulation, expansion simulation, and evaluate. Expanding 2 terms using PTR-based diagnosis can get about 90% of the performance gain, while if we are only using IDF as diagnosis, we need to expand 3 terms. So we are effectively saving users time.
Do you know what the very best you could have done with 2 is?
What do you mean the very best?
I mean, you
with
could
2?
have tried all pairs to see
Oh.
like an oracle.
No, I haven't done that, but that's a good point. So we're using a greedy strategy here. Greedy strategy, not necessarily the optimal. That's right.
No, sorry, I don't think that's what I meant.
Oh.
Or I mean, I know that unless I misunderstood you. So greedily selected the 2, fine, but you have like the 4 or 5 expansions, right? So would you be able to be able to try all 2 and see which one gives the very highest retrieval
Do you mean
score?
expanding which query term, or do you mean how many query terms to expand for each query term.
Which query terms to expand?
Oh, so we haven't tried permutations. We are only using a greedy approach to expand the.
All the possible combinations.
No, we haven't tried that.
Rank them just by performance.
Yeah, yeah.
Accuracy.
Yeah,
Because
yeah.
you already have to do this.
Yes.
It's an
Yes.
Oracle experiment.
Yes, that's an Oracle experiment. So in terms of expansion, forms of expansion, we're comparing CNF expansion versus the traditional bag of word expansion, keyword expansion. As you can see, CNF gets better than keyword. CNF gets better than keyword.
Sorry, what is the traditional bag of word expansion here?
So we are using the same set of menu high-quality expansion terms from the users. But instead of doing CNF expansion, we are combining these set of expansion terms as a group and combining that set of query terms with the original query using a weighted combination. And we have also tried weighting the expansion terms, but that doesn't help much. So we have tried several different ways to do the traditional way of expansion.
The traditional way of expansion, you also assume that the candidate expansions are from CNF expansions? Or
Yes, the candidate terms are from CNF expansion. Yes. I have also tried using a automatic, so the standard relevance model, so standard pseudo relevance feedback method to automatically extract the expansion terms, but that's worse than manual expansion terms. So we show that CNF queries, so the proper diagnosis can produce simple and effective CNF queries. I've also worked on other aspects of the problem, such as improving the efficiency of the prediction. So here we can use a one-pass prediction, so one-pass retrieval, with 3 to 10 times speed up and close to keyword retrieval performance while still retaining 70 to 90% of the performance. That's based on the observation that many of the query terms, for many of the query terms, the term mismatch probability doesn't vary much across queries. So we can use that to speed up our prediction.
Does that mean that you don't need pseudo-relevant documents at all?
No, we are not doing pseudo-relevant feedback in this case. Yeah. So one stage.
But you need a cache sort of for each candidate term. We have this profit.
Yes, we need a cache. But luckily, the training set isn't so large.
Like a uniform model, the only difference is now the probability is the probability of term given relevant document.
Sorry, I don't get your point.
Okay, take it off.
Okay.
So you're predicting from the previous C queries rather than
C query terms.
judged relevant document.
Yeah, with judged relevant
Right.
documents
So
from the training set. So I've also worked on.
Coverage could be a problem.
Yeah, coverage could be a problem, and yeah.
this is TREC.
But luckily, you don't need much high coverage. It's about 50% term coverage gets about 70 to 90% gain. If you have larger training sets, definitely better. We have also worked on structured retrieval using semantic row-based structure. So we can annotate the question, which terms are the target, which terms are the agents and subjects, objects. We can annotate the answer in the same way and try to match the structure, not only the keywords. Right? And this problem causes, this structure retrieval causes a mismatch at the structure level, where because of a switch of the key term, the key verb here, the argument 0 here becomes the argument 2 here. And it's a different target. So we have used an undirected graphical model to jointly learn the field level translation from the question to the answer using the training set, which are basically true question answering pairs. We can learn the translation, and we can predict which are the likely structures given a query. And use the prediction, we can use INRI, Lima search engine, to query these alternative structures. So INRI allows us to query this kind of structure. We can get 20% gain in overall retrieval versus using just the strict question structure alone. Okay, conclusions. This talk is about two long-standing problems in retrieval: term mismatch and term weight estimation. We have provided the definition and initial analysis of term mismatch. Future work would explore new features and new prediction models that would improve our prediction even further. We have showed the role of term mismatch probability in basic retrieval theory and used principled approaches to solve term mismatch. But what about more advanced models like learning to rank, like transfer learning? What does term mismatch play? How does it play out in these more advanced models? We have used automatic ways to predict term mismatch and done the initial modeling of the causes of mismatch, of the possible causes of mismatch. And we have provided an efficient way to predict this probability. Future work should explore better ways to model these causes or other causes that haven't been explored here. In terms of effectiveness in retrieval, we have used term weighting and diagnostic expansion. Better techniques are needed, right? Like automatically expanding the query into a CNF form. Better formalism, like transfer learning, might facilitate us to extend this work into more tasks, like relevance feedback, etc. We have done diagnostic intervention. Diagnostic intervention can happen at different levels of the retrieval process. We are applying the diagnosis at the term level and only diagnosing the term mismatch problem. And we have shown that this guided expansion can help retrieval. Future research should explore the diagnosis of specific types of mismatch problems. Is it because of abstractness or synonyms? It could also explore different problems, not just mismatch, but also precision problems, right? So that we can guide lots of different NLP techniques, personalization, etc., to solve the real problem of the query and to improve. And even further, we can proactively diagnose the user, right? We can see what problem the user is having and suggest searches or results even before the user types into the search engine. So that's my thesis work. I have also worked on lots of other things at CMU, building datasets like ClueWeb09, which is being used by more than 200 research groups worldwide, more than 7 TREC retrieval evaluation tasks. I've worked on the Lima toolkit, which is an open source IR toolkit, which can do lots of fancy things. I've worked on large-scale computing, and I do a fairly popular Hadoop tutorial at CMU. In terms of other research, I've worked on structured retrieval. I've worked on legal discovery tasks, patent retrieval in biomedical or chemical domains, and I have worked on information retrieval for human language technology applications like question answering, or tutoring, or knowledge-based extraction from the web, and information extraction. And with that, I end my talk, and I'd like to take feedback.
More time for questions?
I'll just check if, yeah, go ahead.
Yeah, just one more question. For the semantic rule library, what semantic rule library are you using?
Assert.
Assert.
Are there better labels?
I'm just see. So you are using Probabilistic style library. So there may be some new library, like more some new using FrameNet. So that one have a more specific tags.
I see.
Yeah. using differential.
Oh, okay. I see.
There may be better matches from tag to tag.
Right.
Just like 0 and 1, maybe very specific tag for everything.
Right. So Qing's point is just is that better semantic representation of the text will help solve the mismatch. Yeah. I'll just check who else might have questions during the talk.
Right. If not, thank you. Thanks to the speaker again.